to my YouTube channel. Today I'm gonna talk about camera calibration. So this is the second part of this series of video. First part, like I was talking about OpenPose setup, and it's a very useful video. And if you haven't watched the first part, please watch it. And I will assume that you already watched the first part, and I will just continue with where we left, basically from the last point. So agenda. So as I explained, I already talked about the OpenPose setup in the first part of the video, or like this series of YouTube videos. So today I'm gonna talk about camera calibration, which is the second part right here. So I will just skip the first part and the camera calibration part right here. So there are four main milestones I want to go through. First one is radial and tangential distortion, and next one is camera intrinsics and extrinsics, and next one is projection matrix, and last one is band adjustment. So first point, radial and tangential distortions. So there are many ways to fix the distortions. You can use Matlab, you can use Python or like C++ libraries. There are so many libraries and like repositories available online, but what I usually use is Matlab application because it's really easy and you can actually visualize how it is optimized, and you can adjust the threshold, etc, etc. So it's really nice to use, it's really easy and nice to understand. And so the explanation of the distortion. So basically, if you see the frames, those three frames on the presentation, so you can already recognize that the wall is curved right here, and the board has like curvature right here, and yeah, whatever reason, sometimes camera has a distortion like this. You can see the curvature right here. We want to fix this because you want to calibrate the camera, I mean intrinsics and the extrinsics afterwards, and this distortion will interrupt or like decrease the accuracy of the camera calibration afterwards. So you want to calculate the coefficients or the parameters to fix this curvature. So I will explain in Matlab. So let me just go to Matlab very quickly. So if you go to Matlab and just click apps and expand the panel right here, there is an app called Camera Calibrator. If you don't have it, you can just install it. Yes, and basically you just click on it, and you will see this nice page right here, and you just simply need to add images into this interface. So from the file, so I saved frames of the checkerboard, which is here, checkerboard frames, for example from this camera view. I'm not sure if you can see it really clearly, but basically if you want to calibrate the cameras or like fix the distortions, you want to move the checkerboard around or like in front of the cameras like this. The important point is the curvature is toward, I mean, as you see it, oh okay, sorry, as you see it from the frame, the curvature is heavier towards the edge of the frame. So it's very important like you move the checkerboard towards the edge, of course in the middle, and you want to tilt the checkerboard like this, so that Matlab can calculate the radial distortion or tangential distortion error more precisely. And then from here, you can just select all the frames and you just click open. And there's another interface popping up. You can choose patterns. So there are, I think, 3 choices. But like for this case, checkerboard, and you have to specify the size of checkerboard square. So there are white and black squares, and you have to specify the distance of each square, which is 25 millimeters. And image distortion, you can just play around. If you see the distortion is very heavy, you can put high here, and if not, you can just put low right here, and you just need to simply click OK. And Matlab calculates, or like actually detect the checkerboard first and detect each crossing point between the black and the white boxes, and you will see it after Matlab process all the frames. In total 43 frames as processing right now. If you have more frames, it will get more time, but like I would say for this like a demonstration purpose, like 43 is, I would say, enough. So basically you will get this very nice visualization. So basically this is the 0 point, and Matlab detected the corner of white and the black box really nicely like this. This is the first frame, second frame, third frame, fourth frame. It's very nice detection. And so before calibration, there are a couple of things like you can configure. So of course, like a camera model is like one of them, and if you just click options right here, radial distortion, you have a choice to have 2 coefficients or 3 coefficients. So basically, if you have heavy distortions, I highly recommend going for the 3 coefficients, but otherwise you can do like 2 coefficients. And if you want to have skewness or like a tangential distortion on top of radial distortion, you can just click on this. But for now, I don't see any distortion or skewness on this frame, so I will just go for like a radial distortion. Okay, after configuration, you will just simply press Calibrate, and you will get a very nice visualization right here. So I'm gonna explain the bottom panel right here. So this is like camera-centric visualization, the fixed camera position right here, and you will see the pose of checkerboard right here. And in another visualization, you will do vice versa, fixing the checkerboard pose. You will see the different camera pose right here, but it's not nice to see because the camera is fixed in the place. So this is more easily understand how camera is posed and checkerboard moved around, like in front of the cameras. And the top panel right here, you will see the bar graph or for the reprojection errors. So x-axis right here is just like images. So right now, I'm not sure if you can see it vividly, but the first frame is selected, so the bar is a little bit darker than the other bars. But basically, y-axis right here is reprojection error. So reprojection error is the error between detected to the point and reprojected the point, which is the red point right here. So basically the distance between green circle right here and red points. And the nice function for the Matlab, you can change the threshold, like which frame to be included. So for example, like if I put the threshold right here, those frames which has like more errors than the threshold will be excluded for the further analysis, and Matlab will only Matlab will calculate the radial distortion or like any type of like distortions by only using the frames which has low errors. So it's really easy, it's really interactive, and yeah, I would say it's a really nice application you can use. And after that, if you are satisfied with the threshold, you can export the parameters by clicking here, and you can put like whatever names right here, and if you want to export estimation errors, you can do so, but I don't need it, so I just simply press OK right here, and you will get camera parameters, and here you will get radial distortion and the tangential distortion right here. So it's 2 parameters, but you can have 3 parameters as I explained, and I didn't really include the tangential distortion, so its parameters is 0, right? And nice thing, so I'm gonna explain in the next slides, but I can also output intrinsic metrics, which is right here. So we need these parameters to undistort the point, but I will explain in the next presentation slide. So we came back to the presentation slide, and the next point is camera intrinsics and extrinsics. So camera intrinsics is basically the parameters sit inside of the camera, and basically the parameters you want to know is focal length. So this is the distance between center of focal point and center of camera plane right here. So just like a distance between. And another parameter we want to know is principal point, which is the xy point of this plane. It has to be the middle of the plane. So those 2 parameters are called camera intrinsics, and for the mathematical reason, or like to calculate or like understand the point easier, or the parameters easier, we will usually put those parameters in the matrix. So if you just go back to the Matlab, as I explained, it can also calculate intrinsic metrics. So right here, like we have focal point, focal length right here, x and y, and here on the bottom we have principal point right here. So by using camera calibrator application from Matlab, you can calculate radial distortions, or like radial and tangential distortions, and you can calculate intrinsics, which are needed for undistortion function in Python, which I will show you later. So going back to the slide, and that's the camera intrinsics. And the camera extrinsics, the pose of the camera respect with the world coordinate system. We represent usually with rotation matrix and the translation vector right here. So as if, so let's say there is a world coordinate system right here and the camera points right here. We can represent this camera center point by using rotation matrix and the translation vector. So how far between this distance and which angle camera is looking at. So that's the camera extrinsics. And as I said, if you have camera intrinsics and distortion parameters I showed you in the Matlab, you can calculate or you can already fix the distortion points. So OpenCV has a really nice function called undistort point. You can simply put whatever like 2D points from the frame, and you will put intrinsics, and you will put distortion right here. And I don't know why you have to put the non and the additional actually this is intrinsics parameters. I'm sorry, I just messed up between intrinsics and the distortion parameters, but this is intrinsics parameters you have to put in the end. But I will show you the code, Python code later on, but let me quickly go through the projection matrix right here. So projection matrix is basically the combination of camera intrinsics and extrinsics. And if you know the 2D point and 3D point, you can calculate the projection matrix. So there are many ways to calculate projection matrix, but mainly 2 different ways. So first one is using the checkerboard. So the advantage of using checkerboard is you can calculate the extrinsics, intrinsics, and distortion parameters at the same time. But all the cameras has to see this checkerboard at the same time. So if you have cameras like 360 degrees around, then this option not ideal or like almost impossible. I mean, if you have like carton box and you put the checkerboard with each plane, then it's possible, but otherwise this method is not possible for, if you have cameras like 360 degrees around. But then you can also have this like calibration case, so that all the points right here are visible from all the cameras 360 degrees around you, or like around this camera calibration. The point is you have to know the 3D points here. So let's say this is 0, 0, 0 point. Then next one is 0, 50, 0 point, and 0, 100, 0 point. And you will get 3D points, and you also have to know the 2D points from the camera frame, and those like 3D point and 2D point has to be corresponding, right? So that's the like one way like you can do if you have like cameras around like 300 degrees. So as I said, in this tutorial or demo, like we have like 12 cameras around, so that we chose this method. So as I said, we have to know the 3D points from here, 0, 0, 0 points, 0, 50, 0, and 0, 100, 0 points. So just like quick explanation, like we have a distance of 50 centimeters from bottom to middle and middle top. and the distance between the pole is 100 centimeters. And as I said, you have to have like 2D points. I just put U and V to distinguish from the XYZ point in the 3D. So, but basically U is X and V is Y, and you have to know the 2D points of each like point right here. And this point has to be matched with the 3D points. Then first of all, like you want to standardize the data. I mean, you can just like simply like standardize 3D point and the 2D point because when you calculate the DLT, direct linear transform or transformation, if the coordinate is matched, then the quality will be increased. So you want to standardize the data first, then you want to like reformat this formula I showed you before into like this formula. So basically you will put 3D point XY0 here, and you put the 1, and you put the 4 zeros right here, and you will calculate like a negative x point times 3D x point, and negative 2D x point times 3D y point, and so on. And this is like x point, and this is y point, and you will stack this formula for each point. So x and y is 1 point, and I have like a 12 points as I showed you in the calibration case. There are 12 points in total. So you will stack 24 lines, or like if you're a Python user, you will like append those lines 24 times basically. And you will create a huge matrix, and after that you will calculate singular value decomposition. So this is basically the decomposition technique to extract the meaningful matrices from a matrix. So singular value decomposition can output like basically like 3 matrices out of a matrix, and I will show you the code afterwards. But basically the one of the matrix SVD, singular value decomposition, can output is the projection matrix basically. And of course the data is standardized, so you have to destandardize the data. So if you go to the Python code, I will just quickly go through the camera calibration part. So here you will organize the XYZ point in the 3D in the real world right here, and you will import the 2D points. I mean, it's totally up to you how you like detect the point in 2D. But anyway, like you will get like 12 points in total, and as I said, I used 12 cameras, so 12 points for each camera right here. And I will have to undistort the points because as you saw the frame, you know, for some reasons maybe like a camera frame is like distorted, so just in case you have to calculate the radial distortion, tangential distortion, and you will put it or you have to undistort it. So basically like you will put XY points right here from here, so whatever like points like you detected, you will put like 2D points right here, and you will put camera intrinsics, and you will put distortion coefficient. Yeah, I showed you in Matlab basically. So I showed you both right here, right, basically. So intrinsics matrix and distortion parameters right here. So you will just undistort the point, reshape 12 by 2, and make it to the wrist. And now you will do the DLT camera calibration. Basically you have to have is the 3D points and undistorted 2D points, which is corresponding to the 3D points. So if you go to the function, so by the way, so this all the functions from the GitHub repository. From here, I just like modify the code a little bit, but thanks to this repository, I could calculate the projection matrix and 3D reconstruction much more easily. So I really appreciate this work done by AC Victor. But anyway, you will get like 3D points right here and the 2D points, and you will have to normalize. I mean, like this is actually the standardization of the data, and as so that just like a standardize the data right here. And after that, as I explained in the presentation slide, you have to reformat the formula in this way, and you will append those points. I think it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 points right here. You will stack for the X and the Y points, and in total you have like 12 points, and like you will append like 24 times with this one, and you will create like huge matrix, and you will apply SVD, a singular vector decomposition, and as I explained, it will output 3 different matrix, and we only need to have the last one right here. And extracting this one, you have to normalize the output parameters right here, or like a matrix right here. And the data is standardized, so you have to de-standardize the data, and that's the projection matrix you will get right here. So going back to the presentation slide, right here, so that's how you calculate the projection matrix. And the last part, which is the band adjustment. So actually, to calculate, to apply the band adjustment, you have to do the 3D reconstruction, but I'm gonna explain the 3D reconstruction in the next part of the YouTube videos. So, but the basic idea is using the least square method to refine the projection matrix by minimizing the error between the 3D points and the reconstructed points in 3D. So the function that you can use, so in the library SciPy, there is like a least square function, and you will put the function to calculate the error here, and you will of course like put the projection matrix to define, and variables is just like how you want to visualize the processing, and X scale, I just put like a Jacobian, and the tolerance right here, like how far like you want to optimize, you can just like play around with this number, and the method to optimize the whatever like a matrix like you want, you can just like play around with this like a method, and additional arguments to calculate the error. Of course, you want to have like an XYZ point of the calibration cache and a 2D point of the calibration cache from all the camera views, and it just use like a number of cameras like you used just in case like you want to have like some ideas of like how many cameras you used, and yeah, so just additional information like you have to put right here. But if you know number of cameras already beforehand, like you don't need to put this extra parameter or like argument right here. But basic idea is calculating this error. So XYZ point of calibration cage and 3D reconstructed points of calibration cage, and the difference is the error, and we want to minimize this error to refine the projection matrix. And I will just quickly go through the Python code again. So basically, if you go back to the code right here, like we ended up right here, DOT calibration, and once you have all the projection metrics from all the cameras, you will just append or like create a list of all the projection metrics, and you will also accumulate the 2D point from all the camera views, and you will just stack it, and you will put those parameters or like the variables in this line or like in this function. So this square method function right here, it is from sci-fi optimized library, and basically you just create the function to calculate the error. So the function is right here. So basically you need 3D point, actual 3D point of the calibration cage, and you will do the 3D reconstruction, which I'm gonna explain in the next series of YouTube videos. But basic idea is you will have the 2D points, and 2D points from all the cameras and the camera parameters for all the cameras, and you will reconstruct 3D data, which is right here, and simply you will just calculate absolute error between the 3D point and the reconstructed 3D points right here, and that's the error you want to minimize, right? And then you will have projection metrics which you want to optimize, and this is bubbles I already explained, so the other argument I already explained, so I will just skip it. So then this result right here, we want to only have the projection metrics, so and we want to divide those parameters camera by camera. So we know that projection matrix is 3x4 dimensions, so 12 parameters, and we know number of cameras, which is 12. So the result, the size of this variable is 12 by 12 basically, and you will just like reshape this variable into 12 by 12. So we can see each camera has like 12 parameters, and you can construct 3x4 matrix afterwards. So that's the result, and yeah, if I run this code, you will see the bubbles, like how like each point is like optimized, but the basic, this is like how it works basically, and this is the band adjustment and how you can optimize the projection metrics. And I think, yeah, so this is the camera calibration part, which is the second part of this series of YouTube videos. And thanks for watching, and next video I will explain how you can do this 3D reconstruction. And if you have like any questions, you can just put the comments, and I will try to respond, try to answer the question as quickly as possible. And until then, see you. Bye.